Right. So today, we'd like to discuss about oxygen reduction reaction. Now, I just call it as ORR, and then we will dive into the oxygen evolution reaction. So before we go any further, I would like to discuss about that main, how can I say, the contents of the this reaction. So even though we cover that oxygen reduction and oxygen evolution reaction, our main the focus for the ORR is to discuss about the structure, uh, the function, the relationship. So we will discuss about how surface structure may affect the overall the activity and the stability in electrocatalysis using ORR as a main example. And then in OER cases, we will dive into the how to understand about uh, uh, the degradation in electrocatalysis, especially focus on to the dissolution behavior. And also we will discuss about that the major uh, the concepts that we have to think about when you measure the oxygen evolution reaction uh, as an example. So before we go any further, we definitely summarizes that our topics today. As I mentioned that we will focus on to the two reaction. One is the oxygen reduction reaction. In short, it is so simple that we would like to convert the oxygen to the water, right? And the other counterpart should be the oxygen evolution reaction that we can synthesize the oxygen from the water, right? So this is the very well known the reaction for fuel cell and water electrolyzer. Not surprisingly, we already covers that in hydrogen, right? The importance of the hydrogen is already discussed in the last chapter, that the importance of the green hydrogen production, right? Now, surprisingly, we have to think about why we handle it at the oxygen electrochemistry, focusing on a hydrogen, right? As we discussed before that, the electrochemistry and electrocatalysis occurs the anodic and the cathodic simultaneously. Not surprisingly, if you synthesize that the hydrogen from water, not surprisingly, we need a counter reaction for oxidation, since that the hydrogen production, the hydrogen evolution reaction is the reduction reaction. So some things can be oxidized. Not surprisingly, we would like to oxidize water to produce that the oxygen as a counterpart, right? That's the reason why we would like to handle with the oxygen evolution reaction. Now, surprisingly, when you generate that the electricity from the hydrogen, right? Not surprisingly, you would like to utilize that the hydrogen, right? As an oxidant, right? So you would like to oxidize the hydrogen to produce that the proton. Not surprisingly, there are certain reduction reaction, and we would like to utilize that the oxygen reduction as a counterpart, right? With the proton, which can be generated by the hydrogen oxidation reaction. So this oxygen chemistry is the counterpart with the hydrogen, right? So not surprisingly, the overall the performance has been determined by the not only for the hydrogen electrochemistry, but also oxygen electrochemistry. That's the reason why we would like to discuss about oxygen reduction and evolution as one chapter for the discussion. So let's dive into the oxygen reduction reaction. As I shortly mentioned at the beginning, we would like to majorly focus on to the structure function relationship, the using ORR as an example. So we would like to focus on to the three different the facet with the 111 and 100 and 110, the surface as the starting point what we would like to discuss. And this is the cyclophotometry, and I certain that you are familiar with the shape of this one, right? So let's think about since you observe that the butterfly shaped like this, then you assumes that there is a adsorption and a desorption behavior, right? So I believe you already captured, right? So starting from platinum 111 over here, right? The black curve. And if you introduce that the platinum 3 nickel, and then the surface can be controlled. So not surprisingly, as you can see, there is a different part for the hydrogen adsorption and desorption, and the shape of the OH adsorption and oxide formation also be affected by when you put the nickel on the surface compared to the platinum 111, right? So this is the very well-known paper to discuss about why the 111 surface is better than the other one, right? So this is the first answer that we have to discuss. And second one is why the platinum nickel is better than just the platinum. So we can get the answer using the structure function, the relationship using that single crystal study, right? So we do not want to deep dive every in detail, right? But please keep in mind that we would like to touch that the most important things in each reactions, right? So this is the very well-known, the summary that we have to think about. That this is the cyclophotometry that we already discussed about that the platinum 111 in the black curve and the lead one shows that the platinum 3 nickel, right? So please keep in mind that this shows that a butterfly shape, right, which is the symmetric. Not surprisingly, you can also observe that this butterfly shape, right, and people already know that the which species can be adsorbed in each the potential reason. So this is the proton adsorption and desorption, and it shows that the OH minus adsorption and desorption, right? So let's think about what happened in the basal plane of the platinum 111, for example. So if you the cyclophotometry, right? If you change the potential from 0.05 to the higher potential, at this region, there is a proton desorption, right? So at the 0.05, the hydrogen the proton is adsorbed on the surface, right? So this is the starting point, right? I'm sorry. I think it's much better using that bare one. So now let's think about that the shape of the platinum 111, for example. Uh, so I'm sorry that the uh, shape is not that critical what we observed, but please aware of the black curve, right? So this is the platinum 111, and let's think about what happened at the 0.05 potential. The surface is covered by the proton, right? So like this, the surface is covered by the proton. And if you increase the potential or the like this, the charge indicates that the desorption, right? So proton can be dissolved, right, out the like this. So what about this potential region? Then the surface is platinum is fully exposed by the platinum metal, right? Do you understand? So this, I'm sorry, this is the first region, and this is the second region, and this is the third region. What about the third region? There is OH adsorption, right? So the surface of the platinum can be covered by the OH minus, right? The like this. Like this. So what is the key ideas about oxygen reduction reaction? So let's think about this region first, right? So we would like to discuss about the zeta coverage, right? The zeta means that the how surface of the platinum can be exist as a platinum, right? If there is no any adsorptions behavior, for example, in this region, the region 2, the surface is fully exposed by the platinum, then not surprisingly, the zeta coverage should be 0, right? So not surprisingly, if you focus on this region, the zeta coverage is 0. Not surprisingly, what about in the region of the 1? At the very beginning, the surface is covered by the proton, right? And if you increase the potential, the adsorbed hydrogen, the proton can be dissolved, which means that the surface of the platinum can be exposed, right? What about increase further the potential? Then, as you can see, OH adsorption occurs, right? And we would like to correlate between that oxygen reduction reaction curve with the cyclic Bertamogram, right? So as you can see, the critical point is in region of 1 and 2, there is a high activity for ORR. However, what about that the region 3, for example, when the OH is covered on the surface, right? Certain coverage of the OH is covered by the, certain coverage of the platinum is covered by the OH, then the activity decreases, which means that the current, the total current is governed by the not only for the thermodynamic the parameter, right? So energetic parameter, but also we have to think about that how the active site can be exposed as an active site, right? So please keep in mind, where is the active site? That the platinum, right? What about the platinum OH? The platinum is covered by OH, or if the platinum is covered by the oxide, then there is no site to oxygen can be absorbed, right, on the surface, which means that not only for the energetic part, we have to think about the exposure of the active site, right? So this study clearly shows that the number of the free platinum sites available for the adsorption of oxygen, right? That is the key to get the activity, right? So you have to think about not only just for the how to increase that energetic factor. I do not want to discuss further for the energetic factor further because we already discussed in the last time when we handle with the hydrogen, right? We have to think about, we have to do make the moderate uh, hydrogen adsorption, for example, right? Not surprisingly in here, we definitely handle that the moderate adsorption of the oxygen or OH intermediate, something like that. I do not want to say that it is not important. It is still important, but we have to think about not only for the energetic factor, but also we have to think about that the exposure of the active site, right? So this is the key descriptor that when you designed your electrocatalysis, right? But most of the people do not consider is about this factor, right? Because if you synthesize that the platinum nanoparticle, for example, people figure out that it is platinum. So we can conjecture that all of the surface can be active site. But please keep in mind that if you change the potential, the surface of your active site is no longer what you prepared, right? Which means that you always think about what happened at certain potential. That's the reason why recently people would like to discuss about in situ analysis, right? So anyway, the key idea is we have to think about that the 1 minus zeta term. The zeta means that the adsorption, right? So 1 minus zeta means that the available site for the adsorption of the reactant, right? And we would like to call it as a free platinum site. It can be considered as a 1 minus zeta term, right? So what is the key descriptor for high activity for the oxygen reduction? You have to do increase the 1 minus zeta term, the available active site. And how can we do? If you retard the OH adsorption, for example, when you handle with the platinum nickel, right? So let's think about this is the OH adsorption in platinum, but if you introduce that the nickel, the OH adsorption can be shifted to the higher potential. And if you check once again for the OH coverage, zeta coverage on platinum, when you handle with that general platinum 111, the surface is easily covered by the OH. However, if you introduce that the nickel, then the surface coverage of the OH is much less at certain potential. That's the reason why you can get higher ORR activity, right? So this is the very important analogy, how to discuss about how to design and the active site further electrocatalysis. All right, so we would like to jump into the what about that the other metals, because we confirmed that the nickel shows that the good candidates to decrease that the surface coverage of the OH, right? In other words, if you introduce that the nickel on platinum, you can increase that the 1 minus zeta term, right? What about that the other matter instead of the nickel, right? So people already discussed about that the titanium, vanadium, the iron, cobalt, nickel, something like that, right? And people figure out that there is a optimum matter, right, to control the OH adsorption on the surface of the platinum, right? So this is the very well-known the theory, which is called about the demand center model. So demand theory shows that how the adsorption behaviors that can be described by the center of the demand, but we do not want to discuss in detail. But please keep in mind that by controlling that transition matter, that we can make an optimum for the 1 minus zeta term to get a high activity. Not surprisingly, the activity also shows that the volcano-like shape, right? All right. So, as we discussed that, it is very important. You have to keep in mind that not only for the consideration for the energetic vector, but also you have to think about the the surface available site, 1 minus zeta term, right? So we will discuss about is it real, right? So we would like to confirm that how this zeta term can really affect the overall activity, the further oxygen reduction reaction, right? So now let's think about the black curve. I'm sorry, the black curve shows the platinum 111, right? In this electrolyte is the sulfuric acid, and this electrolyte shows that the phosphoric acid, and this one shows that the perchloric acid, right? So please keep in mind, in the sulfuric, phosphoric, and the perchloric acid, there is a different shape for the platinum 111. Why? As I mentioned that, we have to consider not only for the electrode itself, right? But also you have to think about the cation or anion contribution for the electrochemistry, right? Please keep in mind, depending on electrolyte, it contains the different anion, right? So let's think about what happened, right? So let's think about what is this feature. Actually, we don't know, but we can conjecture that it is related to the adsorption and the desorption because it is symmetrical shape, right? So it is coming from the SO4 minus adsorption and desorption, right? And what about this feature? Not surprisingly, we can conjecture the PO4 minus, right? And what about perchloric acid? There is no direct adsorption on a perchloric anion. So we can clearly observe the OH adsorption instead, right? What about the others? Since that the surface is already covered by the sulfuric anion and also phosphoric anion, you cannot capture the clear the peak of the OH adsorption, right? So not surprisingly, what about that the ORR activity depending on electrolyte? As you can see, in the case of the sulfuric acid, the surface is covered by the sulfuric anion, right? So please keep in mind this gray curve shows the ORR in perchloric acid, right? So the activity is much less compared to the perchloric acid since there is a adsorption in the lower potential region, right? What about in the phosphoric acid? Similarly, we can observe that the phosphoric anion adsorption, so the activity is far below compared to the perchloric acid, right? which means that you have to consider the anion effect, anion adsorption on the surface, and this adsorption may change that the 1 minus zeta term, right? Please keep in mind, adsorption handles, covers that zeta, right? So this adsorption behavior decrease that the ORR activity, right? So this is the very straightforward example that if you modify the surface of the platinum using that the cyanide. So I would like to discuss about this feature once again. This is the cyanide anion, and it can be covered on the surface with a symmetrical the features, right? So this if there is a cyanide adsorption on the surface, the surface adsorption of the sulfuric acid and phosphoric acid can be possible, which means that please keep in mind the left term shows that there is adsorption of the sulfate and phosphoric anion, but if you cover the surface with the cyanide, there is no adsorption of the phosphoric and the sulfuric acid. So let's think about what happened, right? So let's think about what happened in these cases when you adsorb on the surface with the cyanide to inhibit that the anion adsorption. The red one shows that the cyclic voltammetry. Please keep in mind, all the shapes are similar, right? Please keep in mind the shape of the each curve shows that identical with respect to the electrolyte because we can prohibit any anion adsorption, right? This is a striking feature. What about that the ORR activity, right? Not surprisingly, ORR activity is much higher compared to the just the platinum 111, even though the surface is covered by the cyanide, right? So this is the very important, right? So you have to think about that. Which factor? The zeta term is the really important, right? So I would like to highlight once again that the current is governed by the energetic factor, but please keep in mind that the other factor, which one? The surface availability is really important. So you have to do not only control that the surface adsorption, right? For example, if you cover the cyanide, for example, so I would like to show that this figures once again. So if you compare this feature, if you deposit that the cyanide, then the surface of the platinum is less compared to the platinum 111 itself, right? But it can prohibit that the anion adsorption. So the total 1 minus zeta shows the higher compared to the without modification of the cyanide, right? So this is the very important, the message that we can handle that. You have to control the surface site by controlling or by engineering, not only for the electrode itself, but also electrolyte, because the performance of the electrochemistry is governed by the whole interactions between electrolyte, cation and anion in the electrolyte, right? So this is the very important ideas that you have to keep in mind. And not surprisingly, as we discussed that, what about that cation impact for the ORR? So as we discussed that, right? As we discussed that, so I'm sorry, we would like to go back to the slide over here. This slide once again, right? So in this region, we already discussed that the OH adsorption occurs, right? So that's the reason why the activity goes decreases by increasing that the potential, because that the surface of the platinum can be covered by the OH or oxygen species to prohibit the further oxygen can be absorbed on the platinum, right? So the key is how to control the platinum OH, right? For the higher or the lower the activity. And in here, we discussed that if you introduce that the nickel in the platinum, for example, platinum nickel, then you can decrease that the platinum OH binding energy, so you can increase that the overall activity. So in here, for the cation effect, we would like to discuss about is there any crosstalk between the cation and OH on the platinum, right? And so let's think about what happened in the cases. We would like to dive into the two extreme cases with the nickel hydroxide and calcium hydroxide, right? So this is the cyclovoltammetry. And as you can see, all right, that the black one shows that the calcium hydroxide and the blue one shows that the lithium hydroxide. So this one shows that the lithium hydroxide and this one shows that the calcium hydroxide. And not surprisingly, let's think about that the OH coverage. As you can see, the OH coverage in lithium hydroxide is much pronounced compared to the calcium hydroxide. So you can estimate that the surface coverage of the OH is much significant when you handle with the lithium as a cation. Not surprisingly, you can observe that the lithium hydroxide shows that the lowest activity compared to the calcium hydroxide, right? Because that the lithium interact strongly with the OH, which means that lithium cation can stabilize that the OH on the platinum, which means that the surface coverage of the OH is much pronounced compared to the sodium or potassium or calcium. Not surprisingly, what is the impact for the stabilization of the OH? The ORR activity is much less compared to the others, right? So the ORR activity is followed by the how the cation stabilized at the OH on the platinum, right? Not surprisingly, this idea is also effect for the carbon monoxide oxidation or something like that. But anyway, I would like to highlight once again, you have to think about that the surface availability, right? With interactions between the cations or anions or the others, right? So the key is how this type of the cation or anions can interact or crosstalk between that surface that affects that the overall the stabilization of the zeta coverage, which is the key descriptor for the oxygen reduction reaction activity, right? Right. So this is the nice summary that cation, right, interact with the certain OH species like this, right? So we call it as a non-covalent interaction, the cation and an adsorbate interaction. Then not surprisingly, the non-covalent interactions between hydrated alkali metal cations and adsorbed OH, right? So it follows that the hydration energy of the cations, it follows that the lithium, sodium, potassium, and the calcium, sorry. So it corresponds to increase the concentration of the OH adsorption with the cation cluster at the interface. In other words, that this interaction can stabilize that the OH on the surface it increased data set coverage, right? Not surprisingly, the activity goes down, right? Because that the activity is dependent on the 1 minus zeta term as a descriptor for the oxygen reduction reaction. So we discussed that how it is really important, right, to control that surface, focusing on that the zeta coverage for further, right? All right, so that's the reason why it is time to discuss about that what is the electrocatalysis compared to the catalysis, right? So I believe you're already familiar with that, the concept of the catalysis. So we would like to control that the interface or intermediate absorption energy, and we call it as activation energy, right? So this is the very important concept in catalysis. Not surprisingly, this idea is still governed in the electrocatalysis, but you have to think about that, how electrolyte affect that the intermediate or a reactant, right? Because we handle with that the ion and electron separation at the interfaces between electrode and electrolyte. So that's the reason why we would like to call it the electrocatalysis can be defined by the not only general concept of the catalysis, but also we have to think about that what happened in between electrode and electrolyte. That's the reason why we call it as electrocatalysis can be defined as a interface phenomena, right? So not surprisingly, how to design the electrocatalysis, we already know that. In the catalysis, the major description is to control that delta G, the energetic factor, right? So in the catalysis, we would like to control how the adsorption energy can be controlled by the doping or by the certain active site or structure function relationship or something like that. In the electrocatalysis, this factor, right, the energetic factor is still very important, but we also consider how the microenvironment, for example, how the interactions between adsorbate with the cations or anions or interactions with the water, right? So we have to think about that the playground for the electrocatalysis can be extended not only just for the catalysis itself, but also the microenvironment, which can be described by the adsorbate chemical environment. That's the reason why we would like to call it as interface engineering for electrocatalysis. All right, so we would like to further that based on that the model study. Please keep in mind that the old study that we discussed is the single crystal based study, right? Please keep in mind that. So we covered that platinum 111, 100, and 110, and also we extended it to the platinum nickel, and we can further by the modification of the different transition metal, cobalt, iron, or something like that. And also we discussed about how the anion impact for the ORR, and also how cation also impact for the ORR. You're using that platinum single crystal, right? So the remaining thing is how to achieve in the real world the catalysis, because that no one used that the single crystal as application, because that the single crystal is really good model system, but the surface area is really low. So we would like to mimic the idea what we discussed in the single crystal in the real world system, right? So this is the how to bridge the structure function effect to the real catalysis. As we shortly mentioned that the platinum 111 is better for the ORR compared to the platinum 100 and 110. So how to mimic that? So after sputtering, and if you anneal the surface with the hydrogen, then we can make a relatively older surface compared to the other, right? All right, so the how to bridge the structure function effect to the real one, right? So as I shortly mentioned that the heat treatment is really good, because that if you increase the temperature and then during the cooling process, the surface can be reorganized with the lowest surface free energy. For example, the platinum 111, right? So if you anneal on the very reductive condition. So this is the surface before annealing, right? And if you observe after the annealing in the reductive condition, you definitely observe that the surface is the smoothed, right? And exposure to especially for the 111, like smoothing effect that can be observed when you anneal the sample in the reductive condition, right? So you can mimic that the 111 like the smoothed surface in the meso or macro scale by just annealing in the high temperature, right? So this is the one idea how to mimic that the single crystal structure. And how to mimic that the effect in the nanoscale, not surprisingly, we would like to anneal the surface in the hydrogen, then you can make a relatively smoothed one like this, right? So without annealing, as you can see, there is a lots of the defects, right? And low coordinated side. However, if you apply that the annealing, then you can make a relatively well organized surface with the skin type, which is the very similar to the platinum, nickel, or platinum 111, like the structure can be obtained by the high temperature annealing, right? And the other one is how to confirm that a skin structure. We do not want to discuss the deep dive because we do not define that what is the skin, but there is a electrochemical method to confirm that the smoothing effect. So if you're interested about this idea, so please check that the reference, but we do not want to discuss in detail in here. But anyway, there is a way to confirm that the smoothing surface by electrochemical method. And finally, we would like to discuss about how to apply it in the nanoscale with that the platinum 111 or platinum 3 nickel 111 type structure. So this is the very well known report. The starting from the platinum nickel 3 polyhedra, and just by acid washing, then the nickel can be dissolved out and then just form as a platinum nickel, right? Please keep in mind that there is a huge dissolving of the nickel species to improve to make the 3D like structure, right? All right. So this is the intermediate. And if you go further, then you can observe that this nanoframe structure. And not surprisingly, if you anneal the surface, you already captured that there is a surface smoothing effect, right? So from the corrugated surface to the smoothed surface can be controlled by the annealing, right? So you can mimic that. If you increase that the surface of this nanostructure, it can directly mimic that one-on-one like structure, which is the highest activity for the ORR, right? Now, surprisingly, this is a really good for ORR. I do not want to discuss further, but it also shows that the high stability compared to the others, right? And not surprisingly, this is not the only idea. The other groups proposed that the different strategy to increase that the not only activity but also stability, right? So some groups propose that the shape control, and the other groups utilize that the doping, and the other groups also discuss about the others, right? But anyway, there are different strategy to obtain that the high activity and the stability, but the key idea is how to control that surface structure, right? To mimic that the 111, because that the 111 is the most active and most stable for the oxygen reduction reaction. All right. So this is the very short summary about that discussion for oxygen reduction reaction, especially focusing on to the platinum as a model study. And not surprisingly, I believe you already captured that the platinum is a really expensive noble metal, right? So please, I would like to highlight that most studies has been done in the more than 10 years ago, right? Not surprisingly, there's still the good papers are coming, but people would like to jump into the non-noble matter catalysis for the oxygen reduction reaction. So I would like to briefly discuss about that the how to develop that the non-noble the matter-based oxygen reduction reaction, especially focus on to the nitrogen doped carbon, especially for single atom, the iron with the nitrogen carbon in short, right? So not surprisingly, there is a very legendary paper has been published in 2009, and that by just introducing nitrogen on the surface of the carbon nanotube, it shows that the high ORR activity, right? It is very close to the platinum. So this is the boom up, right? To start about what's going on for further. And not surprisingly, there are several good papers are published quite a lot, right? Not surprisingly, at the very beginning, people discuss about the just to utilize that the nitrogen doped carbon, but people realize that if you introduce that transitional metal, especially for the iron or the cobalt, then it can make better, right? So the recently people also discuss about FENC, the base electrocatalysis for the oxygen reduction reaction. So let's discuss about the MNC type. This is the very well known. The M shows that the metal single atom, right? So for example, iron, for example. So this is the expectation of the scheme of that the metal nitrogen carbon. There is a metal core at the center, and there are four nitrogen can stabilize that the metal atom, all right? And it shows that the relatively good activity, and not surprisingly, there's a lots of the research has been focused on to the how to develop electrocatalysis with good activity compared to the platinum, right? So there are lots of the design principle. I do not want to discuss in detail, but recently people would like to control not only the metal itself, but also people aware that the controlling the nitrogen also very important to control the overall activity, right? So there are lots of the very nice paper already published. So how to control that the MNC structure, the focusing on the metal side and also nitrogen side and also the carbon side, right? But as you can see, this is not the synthesis class, so we do not want to discuss about the every in details about how to synthesize. So if you're interested, you definitely check that the Hughes the nice papers is already published. So enjoy with the catalysis. And not surprisingly, there's still ongoing questions about that MNC catalysis because people aware that the MNC is relatively good catalysis for ORR. However, nobody knows that where the active site, right? So some people suggest that the metal center is the active site, right? And the other one shows that the nitrogen is active site, but when there is a metal with the nitrogen, the metal control or change that the nitrogen. And some people still focus that the carbon is the active site, but if you introduce that the metal or nitrogen, it can also affect that the carbon itself. The problem is nobody knows that where the active site because there is no nice model to discuss about where the active site is. But not surprisingly, you have to capture that the activity is governed by the surface area, especially for the microporous structure, right? So most of the work with the MNC is the forming with that microstructure, right? So not surprisingly, people are aware that there is no any correlation, but people found that there is one very nice correlation that the microporous area shows the a good correlation with the water activity, right? But please keep in mind, even though I mentioned that is a nice correlation, but there is a huge scattered inside, which means that people conjecture that the microporous structure is the active site, but you have to also consider the utilization of the microporous as a active site, right? So this is the still ongoing questions that we have to solve. So not surprisingly, people would like to control that the porous structure, right? As I mentioned that, we are aware that microporous site is active site, but there is a limitation for the mass transfer because that, please keep in mind, what is the micropore? Micropores is defined by the size below 2 nanometer in the IUPAC definition, which means that the pore size is less than 2 nanometer, which indicates it is really challenging, right? The mass transport of the oxygen or electrolyte, something like that. So, not surprisingly, it is highly demanded to increase the utilization of the porous structure. And the easiest way is to decrease that the size of the porous structure to decrease that the the pathway for the mass transfer, right? Or people already think about that. What about increasing data or introducing data mesostructure? For example, hierarchical structure can be a good candidate, not only increasing data active site, but also increasing that the utilization of the active site for the ORR. All right, so this is the end of the ORR, and we would like to summarize in short. 네, 그래서 오늘 우리가 그 옥시즌 리덕션 리액션에 대해서 알아봤고요. 그 ORR에서 우리가 주요하게 조금 살펴보고 싶었던 것은 사실은 다양한 관점이 있을 수 있는데 제가 그러니까 처음 시작할 때 말씀드렸지만 사실 요 파트 이런 example 파트는 아직까지도 어떻게 그러니까 뭐 100% 이게 옳다 그르다가 정해졌다기보다는 다양한 이론들이 존재할 수 있고 그 중에 하나를 제가 소개해 드리고 있는 겁니다. 그래서 저희가 ORR에선 제가 중요하게 생각한 것은 이 ORR 자체가 중요하다라기보다는 제가 여기서 강조드리고 싶었던 것은 우리가 일반적으로 그 지난 시간에 우리가 수소를 다룰 때 무엇을 중요하게 생각해야 되냐라고 했냐면 잠깐만 수소 페이지로 한번 넘어가 보면 우리가 지난 시간에 에너제틱 팩터의 중요성을 이 페이지에서 살펴봤었습니다. 그죠? 옥시즌 리덕션, 그죠? 옥시즌 이볼루션, H2O2 프로덕션, CO2, N2, 그리고 이 앞장이 당연히 수소겠죠. 그죠? 수소. 이렇게 델타 G를 컨트롤하는 게 상당히 중요할 수 있겠다. 왜냐면 우리가 결과적으로 액티베이티드 컴플렉스 티오리 관점에서 본다라고 하면 그 액티베이티드 된 것까지 도달하는 데 필요한 에너지가 전체 키네틱을 결정할 수밖에 없기 때문에 이게 굉장히 중요하다라고 해서 우리가 지난 수소 HR 다룰 때 핵심은 뭐였냐면 어떻게 하면 이 델타 GH를 거의 0에 가깝게 그죠? 키네틱 에너지를 극대화할 수 있겠는가라는 부분이었습니다. 그죠? 그래서 이 부분이에요. 그죠? 이 부분이 역시 ORR에서도 중요하다. 그죠? 그 액티브 사이트 하나가 얼마나 액티베이티드 컴플렉스 사이트를 쉽게 유도할 수 있겠는가라는 측면의 그 에너제틱 팩터가 너무나 중요한데 사실 전기와 전기 촉매 반응에서는 이게 전부가 아니다라는 거죠. 왜냐하면 예를 들어서 우리가 ORR은 플래티늄이 촉매라고 하는데 플래티늄이 표면에 플래티늄으로 존재해야지만 여기에 O2가 달라붙어서 반응으로 갈 수 있는데 만약에 플래티늄 표면에 OH가 달라붙거나 옥사이드가 달라붙어 버리면 O2가 더 이상 달라붙을 자리가 없잖아요. 그죠? 그러니까 바꿔 말하면 플래티늄이 플래티늄으로 존재할 수 있어야 된다라는 거고 조금 표현이 이상하지만 즉 바꿔 말하면 플래티늄 표면에 이런 흡착물들이 잘 달라붙지 않아야만 높은 성능을 만들 수 있겠다라는 측면이어서 그러면 이런 흡착종들을 우리가 세타라고 한다면 전체 커런트는 전체 비율에서 전체에서 세타를 뺀 만큼 그만큼이 플래티늄으로 표면에 노출된 비율이겠죠. 그죠? 세타가 아닌, 즉, 흡착종이 아닌. 그러니까 결과적으로 원 마이너스 세타 텀을 증가시키는 게 전체적으로 전기 촉매에서의 활성을 높이는 방향이 될 수 있겠다. 특히 그 반응 조건에서 흡착종이 있을 때, 그죠? 근데 사실 흡착종이라는 거는 우리가 넣어준 N아이온일 수도 있고, 우리가 꼭 넣어주지 않더라도 플래티늄이 특정 포텐셜에서는 플래티늄의 물이 쪼개지면서 그죠? 우리가 물을 제거할 수는 없으니까 그죠? 여기서 말하는 OH 흡착은 물이 쪼개지면서 OH가 붙는 거 아니에요, 그죠? 그러니까 물이 이렇게 달라붙을 수밖에 없다. 즉 우리가 제거할 수 없다라는 거잖아요, 그죠? 그 포텐셜 내에서는 그랬을 때 우리가 그 프로퍼티를 조절할 수 있다면, 즉 물을 더 천천히 쪼갠다라는 거는 OH 흡착 에너지를 낮춰주는 방향이 되겠죠. 그렇게 낮춰주는 방향이 되면 보시는 바와 같이 세타 커버리지를 낮춰줌으로써 1-세타를 높여서 커런트를 증가시킬 수 있겠다. 즉, 그래서, 제가 오늘 ORR에서 크게 강조드리고 싶었던 것은 결과적으로 number of free platinum sites available for the adsorption of the reactant. 그죠? 흡착종 혹은 반응물이 반응에 참여할 수 있을 만한 촉매 표면을 얼마나 많이 노출시키는가가 상당히 중요한 전략이 될 수 있겠다라는 부분에 대해서 오늘 설명을 좀 드렸고요. 그래서 이런 부분들 기반으로 해서 제가 또 하나 강조드릴 거는 이게 진짜 맞냐라는 걸 확인해 보기 위해서 우리가 전해질을 바꿔봤다라는 거죠. 그죠? 황산과 그다음에 인산과 그다음에 어, 펄클로릭 애시드로 바꿨을 때 보시는 바와 같이 SO4-랑 PO4-는 선택적 흡착이 있는 음이온이거든요. 이렇게 선택적 흡착을 하게 되면 플래티늄에서 옥시즌이 반응할 수 있는 자리를 막기 때문에 그죠? 펄클로릭 애시드에 비해서 지금 성능이 되게 낮잖아요. 그죠? 그런데 만약에 우리가 그 표면을 사이아나이드로 흡착을 시켜서 이런 애나이온이 흡착을 막게 되면 오아라 성능이 증가할 수 있겠다. 즉 바꿔 말하면 진짜로 1-세타가 ORR의 디스크립터가 될 수 있겠다. 다만 ORR뿐만 아니고요. 그죠? 즉 우리가 다루고 있는 그 촉매의 그 포텐셜에서 액티브 사이트로 존재할 수 있어야 된다는 거죠. 그죠? 우리가 아무리 플래티늄을 잘 만들어도 그죠? 이 포텐셜 레인지에서는 플래티늄 OH 혹은 플래티늄 옥사이드로 존재할 밖에 없다는 거죠. 왜? 물이 쪼개지니까 그죠? 수용액과 반응하니까. 바꿔 말해서 그러면 핵심은 뭐다? ORR에서는 수용액과의 반응성을 낮추는 게 상당히 중요할 수 있겠다라는 거죠. 그죠? 그래서 우리가 그런 전략들을 좀 취할 수 있다라는 것을 살펴봤고, 뭐 사실 그 다음에는 진짜 짧게 설명하는 겁니다. 그죠? 우리가 단결점에서 배운 걸 어떻게 나노 파티클에 적용할 수 있겠는가에 대해서 짧게 살폈고, 그 다음에 플래티늄을 대체할 수 있는 전략으로서 이제 MNC 스트럭처의 관점에서 살펴봤었고, MNC에서도 사실은 메탈을 바꾸느냐 아니면 나이트로젠을 바꿔주느냐 카본을 바꿔주느냐에 대한 엔지니어링이 당연히 중요할 수밖에 없겠다라는 건 우리가 쉽게 예상할 수 있겠고요. 근데 우리가 이제 뭐 합성 클래스가 아니다 보니까 디테일하게 다루진 않았고, 그럼에도 불구하고 우리가 하나 꼭 기억해야 될 건 이런 대다수의 MNC 촉매 액티브 사이트는 마이크로 포러스에서 만들어지기 때문에 마이크로 포러스 사이트에 우리가 액티브 사이트를 만드는 건 중요하다는 건 알겠어요. 그죠? 근데 액티브 사이트가 액티브 하려면 여기에 물질 전달이 빨라야 되는 거죠. 그죠? 유틸라이제이션이 좋아야 된다. 그래서 이 MNC 촉매 같은 경우에 있어서는 그런 유틸라이제이션의 관점이 상당히 대두되고 있다라는 것까지 간단하게 살펴봤습니다.